Okay, cool. So for this talk, I've given a couple of talks at Devcon. If you listen to my one on Monday, you heard some of the crazy, weird ideas in my notebook. If you listened to the one yesterday, you heard about end-to-end internet games and a couple of new technologies that I think could enable a bunch of insane new consumer crypto apps. But today, I figured for Mud Day, and because this is a classroom, we do something a little bit different, and I take it in a different direction. I figured that today, what would be most interesting and useful to like probably this group of people would be if I just went through a couple of kind of hard/interesting technical challenges I faced building random stuff over the past like year. And better? People can hear me well? Yeah, I figured I'd go through a couple of technical challenges I faced building stuff over the past year and talk through some problems and what they were and what I did to fix them. And so with that, the talk is called, what? Three Things from Building Stuff by Small Brain. And so what we're going to do, because this is a classroom, is we're going to play a game. And the game is called Who's Smarter Than Small Brain? And how it's going to work is I'm going to propose to you one problem that I ran into. And just like for some poetry, it's really fun that these problems exist because the things I build are really simple, right? Like, it's not like you're trying to cure cancer and you have a hard math problem. It's like you're trying to get people to yell at each other over the internet and you have a hard math problem. And there's some of them are going to be math problems, some of them are going to be like solidity questions. And we have very smart people in this room, like Dr. J and Mr. Indexer and Paco and David and Frolic and, you know, our German friend in the back. And so maybe this is going to be really lame and you guys are going to get the answers really quickly. But hopefully what's going to happen is you're going to struggle a little bit, then get the answer, and then it'll be interesting. But please participate. Okay, question number one. We're going to start easy and we're going to go to harder. So question number one is what I want to do is I want to put some money on Ethereum in a smart contract. And then I want to have a password that I give to somebody. And I want anybody with this password to be able to unlock the funds. It's like a really, really simple like escrow smart contract. I put some money in a smart contract, I have a password, and then I give this password to somebody and they can unlock the funds. How do you do it? And while I give you a little bit of time to think, this was useful. Okay, amazing. Well, this was useful for an app I built called Yonk, which was an app where you can send people voice memos with a little bit of payment attached. And if they don't listen to your voice memo in time, Face ID, no headphones, they won't get the money. And the longer they wait, the less they get. And it was used in this app to do invite links. So if we have this primitive, we can actually send people who don't have wallets yet an invite link with a Yonk in it. But anyways, getting back to the question, yeah, does any one of you want to jump in? You want to use your mic? Yeah, what do you think?
Yeah, so mine is kind of a brute force, but what you do is you hash the secret,
yeah.
You put it on chain,
yeah.
And in order to prove that you know the secret, you make a simple ZKP that you know the pre-image of the hash. But
yeah.
It's kind of brute force. I don't know if it's the best way to do it.
No, I think that totally works, and I think this is actually a valid solution. The solution makes sense to people in the room. And Justin, can you explain why it needs to be a ZKP?
Yeah, so do you guys know what a hash is? Like you take some value, you can turn it into a hash, but you can't go from the hash and turn it back into the value. So if you put the hash of the password on the blockchain, you commit to the password, but people cannot recover the password from the hash. And now your problem is, can someone show that they know the thing behind the hash without revealing to everybody else?
Yep.
So if you were to just put the password in a transaction and be like, look, blockchain, if you hash my password, you can you'll get the hash. The issue is people can front run you and like see it in the mempool and front run you. So what you do instead is you make a zero knowledge proof that you know the pre-image of the hash.
Yeah, so that's exactly right. And I think what's interesting here is this is the solution I also initially came up with. And then I was sitting in my room like 4 days before ETH Denver, like, you know, trying to write Circom and being very sad. And like, I felt in my heart that there had to be a better solution. And there actually was. Ryan, do you have was your solution different? It was that one. Okay, yes. Here, I'll run over to you with the mic.
You make a new hash from the address of the sender with the password.
Okay.
Oh, no, never mind. That's not going to work. No.
Okay, cool.
Never mind.
Well, I think there's something interesting there. All right, are we ready for the answer to be revealed, or does anybody have it? Okay, cool. This is how it works. I'm so excited about this one because this is like one of the most elegant pieces of like real world, like simple cryptography I've seen. All right, so the first thing you do is you generate a new key pair. And we are going to call, so like a private key and a public key, pretty much a new wallet. And we're going to call this key an ephemeral wallet, okay? Because like we're just going to use it to make this happen, and we're going to throw it away pretty quickly afterward. All right. So the big insight, and some of you might be seeing the whole punchline now, is is that the private key from this key pair is going to be the password that we give to people. And so what you do is you escrow in the smart contract the money you want to put in and the public key associated with that ephemeral wallet. Then what you do is you take the private key, which is the password, and you give the password to somebody else. You give the private key to somebody else. When they want to unlock the payment, what they do is they take their own address, their own actual address, and sign it with the private and public key pair from the ephemeral wallet, and then they can use that signature to claim the funds on-chain. Because the smart contract on-chain just does a signature check to see that, okay, cool, the person with the password said that this wallet should have the money, so that we should give them the money. And this prevents like front run and all of the problems that the ZKP was solving, because you are signing exactly which address should get the money.
Yeah. So the signature is a ZKP. Like a signature is a zero-knowledge proof. It's not a ZK snark.
Yeah.
So we went too far on the heaviness of the solution.
That's actually a better way to think about it. It's exactly the same solution, but a much smaller proof that shows exactly what you need to, versus like, you know, writing something in Circom. This solution not credited to me, actually. It was deep in the Dymo code, because Dymo uses exactly the same thing for invite links. So, you know, big shout out to DC and Nolan for doing like extremely elegant piece of cryptography to do invite links on-chain. So this is the little trick for fully on-chain invite links. Okay, cool. Little breath. Let's move on to question number 2, which, now that I'm looking at it, is a little bit of a mouthful. But let me take you through the question, and then you can like throw out what you think will be a good answer to me. Okay, this is the problem, and you need to do this again on a blockchain. There's a round, all right? And during the round, people are posting vectors to the chain. Vectors is like a long sequence of numbers. So a bunch of players are posting vectors to a blockchain during a round. And then at some time, it's the end of the round. At the end of the round, an oracle comes and puts another vector on chain. And this is the truth vector. And let's say like the players are like me, Justin, Elena, Frolic, Ryan, etc. What we want at the end is we want the sum of the distance between the Oracle and Justin vectors, and the Oracle and Elena's vectors, and the Oracle and Frolic's vectors, etc. We want the sum, the distances between the truth vector and the player's vectors. Does that make sense? Cool. Okay, any ideas on how you can efficiently calculate this? All right, I need to give you a second to think while I give you context. That's the pattern, so don't jump in just yet. And the formula we're using for distance between vectors, actually we can use anything reasonable. We can literally just use Euclidean distance. But another valid formula, which is a nice little hint for this question, is cosine distance, which is the dot product of the two vectors over the magnitude of the two vectors. All right, sweet. Anyways, the context for this is this app called Tomorrow.news, which is a prediction market for tomorrow's New York Times headline. That's TMR. That pays people out based on how close in meaning they are to the truth. And we use sentence embeddings to do this. So sentence embeddings are a way to turn a sentence into a vector. And when two vectors are close to each other, when two sentences are close to each other in meaning, the vectors are close to each other in distance. So we can actually use this to build a prediction market that's semantic. Anyways, back to the problem. How do you do this nicely on chain? What were you going to say?
Oh, I mean, I don't have a full answer,
Yeah.
but one thing I'm wondering if it's useful is to consider the truth vector to be 0.
Okay.
And then we shift thing by the truth vector. I mean, okay, so as a first kind of like
Yeah.
start, just assume truth vector is 0, and then we're gonna have to reshift everything. That
Yeah.
should make a bunch of the distance stuff much simpler, at least conceptually.
So this is what I thought too, but it actually doesn't, because the truth vector could end up anywhere, and distance from 0 is the vector itself.
Okay.
So it kind of keeps everything exactly the same in your
God
example.
damn it! All right.
Any other thoughts? All right, should I ruin it?
Give us a hint.
The hint is you have to stare. Well, so do we understand like the core problem with this? Like, I guess a question somebody should ask is like, why don't we just sum the distances at the end?
Yeah, are you assuming that you don't want to have an O of n?
Exactly, because we're on a block. I kind of expected somebody to say it, and then I would be like, no. But why we can't just sum the distances at the end is because there might be n players, and then we need to do like, on the order of n computations, and it might brick the game unless there's batching.
So you want a constant time solution.
We want a constant time solution to this problem. All right, I'll give it to you.
Can it be an incremental solution?
What does that mean?
Well, every time someone adds a vector, they do an incremental amount of computation.
Yeah, it can.
Okay. So it would still be O of n, it's just you don't pay it in one go at the end.
Exactly, great. But you don't have the truth vector until the very end.
Is another hint that is done pairwise?
What do you mean by
While
that?
you always do it with respect to the previous vector?
I will give you a hint that you just increment one big value as you go on. Yes. Oh, amazing, thank you.
Oh, thanks. I wonder if this expression can be factorized.
Yeah, how would you factor it?
I see there is the dot product. I'm not sure about if the dot product can be factorized, but I think that you can keep the ones on the side, sum the factor, and then do the operation on the sum.
That's it. That's exactly it. Oh my God, I'm so happy.
The computer is gone.
Yeah, it's coming back. Okay, cool. That's exactly it. What's your name? Bobosh? Great job. That's literally what you do. So here are all your, these things you need to sum. These are everybody's guesses. Like, this is somebody's guess, this is somebody's guess, this is somebody's guess. If you stare at this long enough, you're like, B over magnitude of B is the truth vector over the magnitude of the truth vector. And that's like a common factor in all of these terms. So you can just like pull that baby out. And also all the ones you can just like, pull out to the side of the sum. And then this thing starts looking like, sorry, I didn't math script, but it starts looking like, n, which is all the ones that you pulled out, minus the common factor times like the sum of other stuff. And so all you do is you keep track of the sum of other stuff as people are making their votes, and you do a nice little multiplication at the end, and you're all very happy. The problem with this really is that like what we ended up needing to do is we ended up needing to square everything or actually raise anything to a power we wanted to decide because the distances weren't like crazy enough, and so the market was like kind of boring. And like fundamentally now like this kind of sucks because you can expand this out, actually can use Euclidean distance here, and then because there's a squared and a square root, it like, ends up being kind of nice, but you still can't do it. Because high level, what you did is you like added non-linearities to a thing which we were like, it was really nice that it happened to be linear. And so to do this, there's two things that we aligned on. One was you could do a ZKP using something like SP1, right, to like succinctly verify the sum on-chain later and compute it off-chain. But it turns out that like the cost of doing that on their prover network is actually more than the cost of literally just looping on-chain and doing the sum because the vectors were of such high dimension. And so we actually did end up doing the stupidest thing, which was looping on-chain. Great. All right. Okay. Third question. Third question is a really open-ended question, and there's not like a correct answer to this one. But what it is I guess first is like, are people here familiar with words 3? All right, like maybe like a fourth of you. So I'll go over just the part of the game you need to know to motivate this question. Words 3 is a game where you're playing Scrabble on-chain on like an infinite grid, and you have to buy in letters to play. And the price of buying letters changes with some formula. That formula used to be a VRGDA. That's how the game, one edition of the game looked. It's a bunch of people playing letters, and letters are on different price curves. The pricing curve of the letters used to be a VRGDA with target rates per letter set based on the rarity of the letter. What a VRGDA tries to do, like kind of reductively, is sell a certain amount of things at a certain. So it might be trying to sell one letter per day at a certain price, and if letters are going faster than that rate, the price rises exponentially. And if letters are going slower than that rate, the price falls logistically. And so, you kind of like use prices to push the rate at which your items are sold to the rate you want. The issue with VRGDAs was it had two pretty bad properties, both related to memory. One thing is like it doesn't sustain a lot of players playing at once because prices sky really fast and they never come back down, and it kind of pushes people out from playing. You know, going way too fast from the target rate, that price is rising exponentially. Now there are a bunch of people who want to play and they can't. The second bad thing is if nobody plays for a really long time, prices stay depressed for a really long time because you're like so far off from the target rate that like if nobody plays for a week and then people start playing, you're so far off from the target rate and you should have sold so much stuff in that time that you know, the price is always going to end up being zero. What we want is we want some sort of new pricing function that allows players to like enter at any time, and also like if the game is no activity for a long time, doesn't brick it, still maintains that it's fun to play. And so the open question is like, what is a better way to price these letters? Yes.
Reset daily. Like don't have like an infinite window, have like a floating window for the same formula.
Yeah, I think that's a very valid answer. You could reset the thing daily, so it just kind of works. Oh my God, I knocked water over. You could reset the thing daily, so it just kind of works. I think that's a valid solution. I think like my brain personally just like doesn't like it because it's like kind of inelegant.
Well, you could do a rolling window.
Yeah, so how does
instead
the
of a
rolling window
reset.
work?
I think this is what he was suggesting.
Okay, so you limit the memory of the thing to just the past day.
Yeah. And you roll, so there's no discontinuity, you just roll.
Yeah, I think that would work. I actually quite like that.
Get an investment from Paradigm, and then they can think about a new
Yeah, exactly. They can write new blog posts. Yeah, totally. Any other thoughts? This one, there's lots of valid answers too.
Well,
Yeah, what is it?
What if, so basically buying other letters affect all the other letters? So like, you know, if there was a lot of A's, they keep growing in price, but as soon as somebody bought a single B, a single C, a single D, you just see that the part of the A's among all the letters in the game diminishes, and so the price goes down. So and then you might not even need a rolling window, you just like match every letter against the total number of all the other letters.
Yeah, I think that's another good idea, and I think like specifically what's going on in that idea, and I might have misunderstood you, but specifically the underlying thing that's going on in that idea that fixes our problem is like you shifted your notion of time from actual time to like players buying things. Like one tick is not like 1 second, it is like one buy. And so if there's a bunch of inactivity, the game actually doesn't even feel it. It's just like it started off when the next player buys something.
Wait, but isn't it circularly defined? Because if you say, I want to sell 4 letters per unit of time, if your unit of time is amount of letters sold.
Well, it wouldn't work with the VRGDA.
Oh, okay, I see,
Right.
okay.
Yeah. I agree it wouldn't work. In that case, like it's just always going to be on the line.
Yeah, it's just linear, right?
Yeah. Okay, I have a minute left, so I'll give you what I ended up doing. I don't think this one's the answer. I think it's a answer. What I ended up doing is like drawing this little curve in Desmos. And how this curve works, I'll go point at the screen at this side this time. How this little curve works is like this is time, this is the price, and whenever you buy, it just like jumps a fixed amount of X on this curve. That makes sense? And so why this is really, really nice is like, and up here, right, like around $300, this line is straight up. And so if like somebody buys at $300, the price is gonna like sky like crazy and then fall down super fast. And then like around here, like the price is kind of never gonna get lower than some amount of time, than like whatever this is, I think like around $10, like kind of no matter how long the game goes. And so what you get is you get like really interesting gameplay in this area. If the price starts getting pushed up like crazy because a ton of people are playing, it like falls really fast so that people can enter again. And if the game's inactive for a really long time, it still stays somewhere down here and like can jump up the curve pretty fast.
Do you bound it so it doesn't go too far on the right? Otherwise, you still have to catch up by. You still have the problem of the VRGDA, which is the price has gone too low. You have to catch up by buying a ton.
Sorry, it didn't move forward by a fixed amount. It moved forward by a percentage of how far back it had been.
Okay, it makes sense.
Yeah, and it moves forward. That's linear, and the curve is exponential, and so you get your difference. Yeah, good catch. Right. But that's how this works. And that's what ended up being deployed. One really bad thing, well, I don't think it's bad, but like one criticism of this curve was that like you can't really get letters above like $500 or $600 because like literally you can't buy that fast. And so it kind of puts like, it's like an upper bound on the price of like how high things can go. Again, which I thought was reasonable, but some people did not react well to. Anyways, that's talk. I hope you learned something. This is me and the best way to contact me.
All right, question time. So Small Brain asks questions to you. Now you can ask questions to Small Brain. You can have your revenge.
There's one question.
Which
is
is Big Brain.
Amazing. Thank
Great,
you.
thanks for your contribution. Okay, so you can either pose the question by scanning the QR code or you can raise your hand, we'll bring you a mic. Either works.
Yeah.
How important is it for players to understand these formulas, like especially for the last one here?
Yeah.
How do you think about that?
I'd say like the other two, it's like really, really not important. Better? Oh, the question was how important is it for players to ask these formulas, to understand these formulas, specifically the last one. So I think like the first two, it's actually like really not important for players to understand like how this is done. It's like honestly an implementation detail that like makes the thing work on chain. For this last one, we still didn't really want players to I don't think we I didn't like want players to have to understand it. The idea should just be like you jump in and you buy and you see prices going up and you like kind of feel the curve. But I think like if you're like a Words 3 power player, which there definitely were, you know, you go in and you understand how the curve and the math behind the curve works. And that one's like, and I think like if you have a strong understanding of how the curve works, it does give you an advantage in the game in the last case. Yeah, that's another thing too, is like there's lots of complicated constructions that are better, but like you also want your construction to be like as simple as possible for these in. And so, you know, trade-offs.
We have two questions that have to do with past projects.
Yeah.
So one is, what is the next plan for network state? And then the other one is, what's happening with Words 3 in terms of users currently?
Yeah, both are good questions. I think in Words 3 in terms of users currently, I think they're like 2, it's not much. And like Words 3 tend to have like a bunch of activity the first couple of weeks and then kind of petered out. I think like it will come back. Like there's like clear things to fix. I think like one thing I'm focusing on, the next time it has to come back, like, you know, there's like, I feel like there's 1,000 people in crypto who are like excited about the things I make and play them actively. It has to be really clear to me how like a larger audience past those people like can get excited and be pulled into it. And I think like until I figured those problems out, there's not gonna be a big push to relaunch it. Yeah.
One question, which is from someone that joined late, is any of this stuff implemented?
Yeah, all of this stuff is implemented in open source on my GitHub. In fact, it's not only implemented, it's like on mainnet, and people have like spent on it and played the thing. So, you know, it's implemented all the way.
One question that has received quite a few votes is, what's your next project?
The next project is a talking duck, which you like will grow up over a month, and you can like pat it on the head to influence its personality. That's what it is.
And there's actually a question related to that, which is, when can I buy a talking duck?
Now, if you want to, you can find me and like Venmo me $30.
What about people that don't have Venmo?
You can Dymo me $30.
Great. Why are you called Small Brain?
It's a good question. I mean, I think it started off as one. It was funny. David came up with the name, by the way. So big credit to David. I think it was because it was a couple of things. I was searching for what to call like the name that would launch all of these experiments. And one, I wanted people to like not take it too seriously, right? And also like it was a little bit of like the first time I deployed something, it was unaudited. I like tend to take security a lot more seriously now. But I was like, this was like my audit. It was like, all right, it was deployed by like a small brain PFP, like you can't get that mad at me if there's a bug in the contract, you know. So that was like maybe 50% of the reason why. The rest of was that I just like really liked the name and the logo.
Yeah, and Small Brain found a bunch of bug in mud as well. So it's been kind of a massive bug bounty. Someone is asking what's your demo address.
What's my demo address? I don't know if I think it's like SBG. Just literally find me after and I'll confirm.
Okay, no more questions digitally. Anyone has a question in the audience, raise your hand and we'll bring you a mic. Nope. All right. Thanks. Another round of applause.
Thank you.
All right.